let's review some things that you learned about logs, and hopefully logs will make more sense to you after we do this quick review. So let's just look in general at what a log is made up of. We have log with a base b. Notice the b is written below. Like if you were thinking I was writing on a line, on lined paper, the b goes below the line. Okay, so I'm going to take that off so it doesn't get in the way. Log base b of x, so that's inside the function, usually we put that in parentheses, equals y. So what does this tell me? It tells me if I take b and raise it to the y exponent, I will get x. b to the y power equals x. So a logarithm, the logarithm equals an exponent. So this number over here is always an exponent that I put on this base. So if we look at some examples, I think this will help. So if we look at the first example, 3 raised to this power gives me 81. So what I'm asking is 3 to what power equals 81? Well, if you remember, the 81 is 9 times 9. That's going to be 3 times 3 times 3 times 3. So it's 3 to the 4th. So this would be 4. 3 to the 4th equals 81. Okay, the next one, b. 3 to what power gives me 9? 3 to what power gives me 9? That's probably pretty easy for you. That's 2. The third one, 3 to what power gives me 3? Well, that's 1. So I want you to notice whenever the base and the argument of the log, or the number that's inside the log, are the same, the log is always going to equal 1 when these two numbers are the same. Okay, the third one, 3 to what power gives me 1? Oops, I'll switch back to my black here. 3 to what power equals 1? Well, that's 3 to the 0. So once again, I want you to notice that if the argument inside the log is 1, then the log is always going to equal 0 no matter what the base is. 4 to the 0 would be 1, 10 to the 0 would be 1, any base to the 0 would be 1. Okay, the next one, 3 to what power is equal to 1/3? Well, that's -1. We just learned that when we talked about exponents. Okay, 3 to what power is equal to 1 over 27? Well, think 1 over 27 is 1 over 3 cubed. So I would have to make 3 to the -3 power to get 1 over 3 to the +3. So 3 to the -3 power is 1 over 3 to the +3. So notice that when I am, these numbers are a fraction of the base, or a fraction of the base raised to some sort of power, these are negative numbers here. When this is 1, so numbers greater than 1 for these bases have positive exponents. Numbers less than 1 have negative exponents. What about 3, the next one? This is saying 3 to what power equals 0? Well, notice that if I use positive exponents, I get positive numbers inside here. If I use negative exponents, I'm still getting positive numbers inside here. There's no way to get 0 by raising 3 to a power, so this is undefined. The next one is 3 to what power gives me -3? Once again, there's no way to raise 3 to any real number power and get a -3. It turns out this is an imaginary number, but for right now we're just going to consider it undefined in the real number system. This should coincide with the logs, the log graph. Actually, let me draw that a little better. If you recall the shape of the log graph, remember that the y values, okay, and these are the x values, what's inside the log. The x values can be only positive numbers, not 0, okay? So x values are going to be positive numbers. Notice that the graph does not touch the y-axis or cross over into the negative values for x. They're all positive values for x. I am going to leave these as a homework exercise for you, and I will come back later and talk about them. Okay, now let's go to section 3. Now what's different about section 3 is I put the x now in different places, but we're still going to write this the same way we did before. We're going to say the base raised to this power equals this. So base raised to this power equals this. So I'm going to say x to the first equals 5. So what is x? X equals 5. Then I'm going to say 10 to the 0 power equals x. What is x? X has to equal 1. 16 to the 1/2 power equals x. Well, that's the same thing as saying the square root of 16 equals x, so x equals 4. Remember, we can't, even though we can think of square root being plus or minus the square root, remember this number in here can't be negative, so we can only be positive 4. The next one, x to the negative 2 equals 1/4. Well, one thing we could think of is x to the negative 2 is the same as 1 over x squared. Well, if 1 over x squared is 1/4, what would x have to equal? X would have to equal 2. So 2 to the negative 2 is 1 over 4. 2 to the negative 2 is 1 over 4. That checks. Okay, next one. 2 to the 5th equals x. 2 to the 5th equals x. And we did one recently where we saw 2 to the 5th. That's 32. Actually, it was a different video, but recently for me anyway. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. I was counting on my fingers in case you couldn't see me. Next one, x to the 0 power equals 1. And you're going, well, wait a minute, x could be anything, couldn't it? Well, that's actually a pretty good answer, except there are some restrictions. X cannot be a negative number, because even though a negative number raised to the 0 power is still 1, we are not allowed to use a negative base. So x is any positive number except x cannot equal 1. Now let me explain why x cannot equal 1. That's kind of an odd thing maybe that you're thinking about, but let's actually picture if x were 1. In other words, even though 1 to the 0 is equal to 1, and that's a true statement, I'm not allowed to use 1 as a log base. So let me tell you why. So this is just a little bit of an aside here. It's not really dealing with this particular problem, but just in general, why I can't use a log base of 1. So let's say we have log base 1 of x equals y. In other words, 1 to the y power equals x. And let's put some values in a table of value for this. So since y is the exponent, it's easier to choose some numbers for y. So let's say y is negative 2. If y is negative 2, x is still 1. Because 1, well, let me start with some positive. If y is 0, okay, 1 to the 0 is 1, x is 1. If y is 1, 1 to the 1 is 1. If y is 2, 1 squared is 1. It's true if y is negative 1, then I would get 1 over 1 to the positive 1. Anyway, 1 to the negative 1 is the same as 1 over 1 to the positive 1. It's still 1. So if this is negative 2, y is still 1, or x is still 1. If I plotted these points on a graph, I'm saying when x is 1, y is 1, 0. There's 1, 0. Here's 1, 1. Here's 1, 2. Here's 1, negative 1. Here's 1, negative 2. I get a vertical line. Not only is a vertical line not a log graph, you can tell it's not the shape of a log graph at all. It's not even a function. So it is impossible for the base to be 1. So we can't have a negative base. We can't have a base of 1, but any other positive number would work for the base. Okay, back to G. X to the 1/3 is equal to 3. So that's saying the cube root of x equals 3. Well, I can quickly figure that out by just cubing both sides. In other words, x has to equal 3 to the 3rd, so x is 27. The last one, here we've got actually a little function to solve. X minus 1 to the 3rd power equals 125. Well, then I can take the cube root of both sides and say x minus 1 is equal to 125. X minus 1 is the cube root of 125. Well, the cube root of 125 is 5. 5 times 5 times 5 equals 125. So x equals 6. Now if we go to the next page of this, I want you to look at number 4 here. I'm going to leave number 4 for you to work on. I may come back and show that to you, but let's look at number 5. Number 5, we need to know a couple helpful things, and this is actually something you'll need to know for number 4. One thing to know is that we have something called the common log. The common log. The common log is log base 10. Oops, I wanted to write log first. Log base 10. Log base 10 we always just write as log. So if you don't see any base number, it's a log base 10. Just like when we do a square root, we don't write the root number next to it. We just assume it's a square root because it's the most common one. The second one is called the natural log. The natural log is log base E, and it's abbreviated LN, and you might think, well, why don't we call it NL instead of LN? Well, this is log naturel. In French, you put the adjective second after the noun, so this is log naturel. I think that's where it comes from. Now, E is just one of these really special numbers like pi. E is 2.71828 ... No repeats, no terminating. It just goes on forever. E is an extremely valuable number in calculus and other upper level math, and so we'll be doing some things with E. It turns out to be very important in math, just like pi is. So you're going to see those two, and those are actually the buttons on your calculator. You have a log button and you have a natural log button, or at least a function above another button. I don't think it's actually a button. If I remember correctly, I think you have a 10 to the x button and maybe an e to the x button, and then above it, if you do the control button, then you'll have a log and a natural log, something like that. I have to look at, actually we could look at the calculator. Why am I thinking about this? Okay, so yeah, there's your 10 to the x with a log above it and your e to the x with a natural log above it right here. Okay, we satisfied that curiosity. All right, so when we look at this, log of 10 to the 6th equals x. Well, this is log base 10 that we're talking about. So you can think this is a log base 10. So we're saying here that 10 to the x equals 10 to the 6th. Hey, x just has to equal 6. So notice if the base here matches the base here, then these two numbers have to be the same. Actually, I'd really rather rewrite that. Let me just rewrite this a little bit because that's kind of messy. I'm going to say over here log base 10 of 10 to the 6th equals x. So when I see that these two are the same, these two are going to have to be the same because 10 to the x has to equal 10 to the 6th, so x has to equal 6. Now, natural log of e to the negative 2. Natural log, remember, is log base e. So log base e of e to the negative 2 equals x. Notice that natural log of e isn't just log base e. Natural log of e is log base e of e. Okay, so I have to actually rewrite it that way. Eventually you'll get used to not even having to rewrite it. Okay, so I'm saying e to the x equals e to the negative 2, therefore x has to equal negative 2. Okay, so natural log of e, well, we'll get to that in a minute. Okay, maybe I'll just say this now. Natural log of e is equal to log base e of e. And that's just 1, because e to the first equals e. Log of 10 is equal to log base 10 of 10, which is just 1. So if you see natural log of e, that's 1. If you see log of 10, that's just equal to 1. But the one you're going to see the most is this. The natural log of e is 1. Now this is the natural log of e to the negative 2, so that's not just 1. But we'll learn a rule that helps us with that later. Oh, this one's interesting. 2 to the log base 2 of 8 equals x. Okay, so what are we going to do with that one? Here's what you need to think about on this one. You have to think log base 2 of 8 is the exponent that I put on 2 to get 8. Okay, so what exponent do I put on 2 to get 8? Well, 2 to the third is 8. So this whole thing, log base 2 of 8 just equals 3. 2 to the third equals 8. So really what I'm saying here is I can say, you know, actually I think I'm going to have to save this one because I haven't taught you guys this yet. How about that? I haven't gone the other direction, but now I guess this is good. So I'm going to actually end this video and then I'm going to come back and do a couple of these problems because these are a little bit trickier.